On your next homework, you're going to be building an ALU in Logisim, so we should talk about what the ALU is and what Logisim tools you're going to need in order to build one. ALU stands for Arithmetic and Logic Unit, and it's the most important component of the CPU because it's where the actual math is done. In general, the ALU takes two binary numbers as inputs and produces one binary number as output. The ALU is capable of performing many different arithmetic operations or logic operations on the numbers that it receives as input, and so it also needs to take an opcode, which tells it which of the possible operations it needs to perform on a given input. Today's other video goes into much more detail on some of the arithmetic and logic components that are part of the ALU. So in this video, I want to focus on how those pieces are put together and how we can simulate that in Logisim. In my Logisim project here, I have a subcircuit for the ALU, and you'll note that when I place it on the main canvas, it has this special shape. In Logisim, you can set up the appearance of a circuit when it is placed as a subcircuit on another canvas by right-clicking the name of the circuit and choosing Edit Circuit Appearance. Here I've zoomed in on the appearance for the ALU, and I used these tools up at the top to create a shape that approximates the standard symbol for the ALU, and then I moved the input and output pins to the right locations on that shape. If I select one of the input pins for the circuit here on the appearance editor, then in the bottom right-hand corner, I get a miniature overview of the canvas where this circuit is defined, and it highlights which input pin I'm currently moving. Let's now take a look at the actual ALU circuit. And when I double-click, we see that currently this is just an empty circuit with two input pins and an output pin. But we said that the ALU takes as input two binary numbers. And in general, we want to do our arithmetic and logic on multi-bit numbers, not just on a single bit input. We can give this circuit multi-bit numbers as input by selecting our input pins and changing the number of data bits. Currently, the data bits for this input pin is 1, but if I change it to 8, then we will have as our top input to this ALU circuit a collection of 8 different bits. Likewise, I can change the data bits for the second input to 8, and I can also change the data bits for the output to 8. And so now, my ALU is a circuit that takes as input two 8-bit numbers and produces as output another 8-bit number. And if at this point I draw wires on the canvas extending from these various inputs, these lines now represent actually a bundle of 8 wires, each of which is carrying a 0 or 1 for one of the positions in this binary number. We are receiving, as this first input, 8 different bits that are each carried on a different wire, but those wires are all bundled together in one line that we draw on the Logisim canvas. And so, if we were to add a logic element to our ALU, like an AND gate, as usual, I'll change the number of inputs on my AND gate to 2. If I were to connect this up to both of the inputs from the circuit, then our wires turn orange and we get an 8 at one end and a 1 at the other end, indicating that what's coming out of this input pin is a bundle of 8 wires, but what this AND gate is expecting as input is a single wire. And so We can't hook up our circuit this way. This won't work. These are incompatible bit widths. But many of the built-in logic gates in Logisim have the ability to handle multi-bit inputs. If we select this AND gate and change its data bits, then our orange wires and our warning go away. And now if we connect the output of this AND gate with the output of our circuit, we see that the AND gate is also outputting an 8-wire bundle that's compatible with our output pin. Now if we use the poke tool, we can modify some of the individual bits of this input. We see that this AND gate, which takes our two 8-wire bundles, is producing as output the bitwise AND of these two inputs. So under the hood, this 8-bit AND gate actually has 8 different 1-bit AND gates, where the first one is ANDing together the first wire in the two bundles, then the next one is ANDing together the second wire, and so on, producing the 8 different output bits, and we get the bitwise AND of these two inputs as our output. It's worth emphasizing a difference in terminology here. We saw an example in our in-class activity last week of an 8-way AND gate, which means that we had 8 individual 1-bit values, and we were ANDing all of those together to produce a 1-bit output. Here we have a 2-way AND gate. Each of the bits is being ANDed with only one other bit, but the bit width of this AND is 8 because we are in parallel performing 8 2-way 1-bit ANDs. So the number of ways is how many distinct bundles of wires we have coming in, and the bit width is the number of wires in each of those bundles. So this circuit can now perform one logic operation, but the ALU as a whole is responsible for performing many different arithmetic and logic operations. So we'd like to have this circuit capable of also performing other possible operations. And we can do that by adding more subcircuits that we will combine into our eventual ALU. So I'm going to right-click on the name of our project and add a circuit. And since we wanted to do some arithmetic, I'll put in an adder circuit. In our in-class activity, you will build an adder circuit yourself, but for now, I'd like to take advantage of the built-in adder circuit that Logisim provides. That's located in the arithmetic heading, and I can choose an adder. And let's zoom in on this a bit. So this adder circuit has carry in and carry out bits, and we can select the number of data bits that we want to add. We'll leave that as 8, since we have an 8-bit ALU. And now, if we add some input pins, we can connect those up. And once again, we need to change our input pin to have a bit width of 8. And we also want an 8-bit input for the second thing that we are adding. And then we'll also want an 8-bit output. This adder circuit also has 1-bit input for the carry in and a 1-bit output for the carry out. But if we're okay with having the carry in be 0, and if we don't need the carry out, then we can just leave those wires unconnected. And now, returning to our ALU circuit, we can zoom back out, and we can now place our adder as a component within our ALU circuit. And if we want to add the two inputs to the ALU, we could connect the bottom input of the adder to our bottom input of the ALU, and the top input of the adder to the top input of the ALU. And then we'd like to connect the output of our adder circuit to the output of the ALU, but the output of the ALU is already connected to the output of our logic element. So what we need here is a way of selecting between the different possible outputs of the ALU. And we can do that with a multiplexer circuit. Multiplexers are found under the plexers heading in Logisim, and I can select a multiplexer. And with multiplexers, we typically want to turn off the enable. That's not going to be relevant for any of the multiplexers we'll be using. And so now this multiplexer has two inputs for data, one input for select, and one data output. By default, this multiplexer has one select bit, which allows us to select one of two possible inputs. If we change the number of select bits to 2, we get a larger multiplexer, or 3, we get still larger, and each time we add an additional select bit, we are doubling the number of possible inputs to this multiplexer. But here, since we only have two values that we want to select between, the output of the AND or the output of the plus, we can have our multiplexer use only one select bit to choose between one of two possible inputs. This multiplexer also has a data bits feature, and so just like our other gates and pins, we want to set the data bits to 8, which means that each of the inputs to this multiplexer will be an 8-bit bundle of wires. And so this means that we can take the 8-wire bundle from the AND gate and connect that to one of the multiplexer inputs, and we can take the 8-wire bundle from the addition circuit and connect that to the other input of the multiplexer, and we can connect the multiplexer's output to the output of our circuit. So now the multiplexer will choose one of its two inputs to be its output, and which one it chooses will be based on the select bit that it receives as input. And so we need some way of providing a select bit that tells us which of these two possible things that the ALU can compute we want to output. We do that by having an additional input to the ALU, which is the opcode. I'll add another input, and I'll change it to face north, and connect it with the multiplexer's select bit. Let's give this a label of opcode, and we can put the label on the south side of the pin. And now if we go back to editing the circuit's appearance, we can choose where on the circuit do we want this new input to appear, and we want our opcode input to show up from the bottom edge of our ALU circuit. And now back in main, we can connect up a wire to that opcode input. So now, if we use the poke tool and toggle the opcode, we see that the multiplexer passes through a different value to the output. When the opcode is 0, the multiplexer passes through its top input, which is the output of the AND gate that we saw before, the bitwise AND of these two inputs. But if we change the opcode to 1, now the thing that's being output is the bottom input to the multiplexer, which was the output of our adder circuit, and so this is the sum of these two binary inputs with the carry out thrown away. And returning to our main circuit, we can now give 8-bit inputs to our ALU. We'll change the data bits to 8, and we'll copy and paste to make another. Connect both of these up, and now if we give an opcode to the ALU, and give it an 8-bit output. If the opcode is 0, then the ALU will compute the bitwise AND of its inputs, whereas if the opcode is 1, the ALU will compute the sum of its inputs. And so this, in general, is how the ALU is made to perform many different arithmetic and logic operations. What's going on inside the ALU is that the inputs are being passed to many different subcircuits in parallel, and then at the end there is a multiplexer which, based on the opcode, decides which of those subcircuits will have its output passed along to the output of the ALU. While editing, I realized that I had forgotten to mention that this opcode corresponds to the values that your assembler program was outputting. When we translate an assembly instruction into hex, some of the bits of that hex code correspond to the opcode that will be fed into the ALU to determine which arithmetic or logic operation the ALU is performing. Let's take a look back at our adder circuit, because in our in-class activity, you will be building your own version of an 8-bit adder from scratch. And so, when we build it from scratch, we can't rely on Logisim's built-in adder component. And so, if we're going to build this out of basic logic gates, we're going to need access to the individual bits of each of these bundles. Let's make ourselves a little more room to work. And if I want to access the individual wires that make up this bundle, I can do that using a component called a splitter in Logisim. The splitter lives under the wiring menu, and I can choose a splitter and place it on the canvas. And the splitter has a bit width in setting and a fan out setting. So if we want to connect an 8-bit bundle to this splitter, then we need to set its bit width in to 8, and now this splitter is expecting a bundle of 8 wires as its input, and if we zoom in on it, we see that what it has done is split our 8-bit bundle of wires in half. We now have one bundle that is wires 0 through 3, and another bundle that's wires 4 through 7. That was based on the fan out setting of the splitter. If we had instead set the fan out to 4, then we would get 4 bundles, each of which contain 2 of the 8 wires. And if we want each wire individually, we can set the fan out to 8, the same as the input bit width, and now we have a separate wire for each of the 8 bits that made up our input bundle. If we similarly split our bundle for the other input, then we can use logic gates to combine, for example, the 0th bit from each of these inputs in order to figure out what should be the 0th bit of the output. Once we have computed the individual bits of the output, if we have a bunch of individual wires that we want to recombine into our output, we can do that with another splitter. So I'll again take a splitter and set its fan out to 8 and its bit width in to 8, but then I will change the direction that the splitter is facing, making it face west. Now we have the output as an 8-wire bundle that we can connect up to the output of the circuit, and based on the individual bit wires that we built up in constructing our adder, we can connect those to the individual inputs to this splitter to recombine them into our output bundle. In the in-class activity, you'll start by building a half adder, which adds 2 1-bit values. Then you'll use your half adders to build a full adder, which adds 3 1-bit values. Then you'll combine multiple full adders into a multi-bit adder that you can use for this adder circuit as a part of the ALU. So when you do this, it will be very helpful to add additional circuits that you can treat as subfunctions that let you think at different levels of abstraction within the circuit. And then, when you put them together, you can build a more complex circuit out of those smaller components to do something like 8-bit addition, and then you can combine many different 8-bit operations together into an ALU that multiplexes between many different possible operations. And this will be the basis for the task that you will eventually be solving for homework 3.